Okay, so last video we talked about. No. Okay, so last video was the first half of thin lenses, or the intro and the thin lens types and the equation, and I worked out these two problems. So now we're on lateral magnification, and magnification is something you've seen before in the previous chapter. So magnification tells you how much something kind of changed in size. So if you have a positive, so if a number is 1, if m is 1, then that means no change. All right, this delta just means no change. Like the size of it stays the same, and m greater than 1 means that it was magnified, right? And then an m that's less than 1 means it was minified. And if an m is negative, that means it was like kind of flipped over the optic axis. So it was, we call that inverted. Okay. So m can be calculated in a lot of ways, so that's useful. If you have the divergences of like if you have the object and image divergence, you can calculate m, L over L prime. You can also say this is probably more intuitive, it's just h prime over h, which is the new size over the old size. So let's call, for example, if you had something that was, the new image is 10 feet high, or 10 meters high, and it was originally 1 meter, then it makes sense that your magnification is 10x, right, or 10. So just plugging in some numbers there. But here we can also say that m equals n times x prime over n prime times x. And so that's what this little thing here, in air, you can treat m as just x prime over x, because in air, you're just n, and n prime is just 1 over 1. So that's this bit there. There was a previous example in the last video where, since we were calculating magnification and it went from a different medium, I remember using this equation. But when you're dealing with the problems where you just have a thin lens in air and nothing else, you're just going to use you're just going to use x prime over x. So this first problem is for a -5 lens. What is the location of the image? So a lot of these problems are really step by step. You have a lens, you have information about either the object or the image. Use that to find the object or image distance or the height. So let's draw this out. I kind of already did. A -5, so I drew this notation. And we don't really care about surface. This is already the overall, this is dt. So we're not worried about like finding d1 and d2 or anything like that. It's just dt is -5. So we're going to use this equation again. L plus d equals L prime. And I like to lay it out so that I see that L is this area, D is this lens, and L prime is this image area. So L is 1 over -1 because you have this in air. We were given a distance of 1 meter to the left. So that's -1, and then the D is -5. Oh, the real object is right here and is 4 centimeters high and is -1 meters away. So we get a new divergence, which is -6, and then x prime is negative 0.167 meters, and that's about right here. I know that because this is 1 meter, so kind of trying to draw it to scale. So the virtual image is over here, and it's virtual because it's on the left side. What's next? Calculate m. Well, you can use m. You can use a x and x prime if you really wanted to, or you can use divergence. I just chose to choose divergence. Is -1 over -6, so you get 1 over 6, and that kind of makes sense because it started out. Oh wait, no. Yeah, that makes sense because it's minified, right? It's minified and it's also erect. I mean, I know that because this is a positive value, so that's why I drew the VI to be like this and not the other way around. So if you look at the rules over here, this is we had a real object in a minus lens that causes a virtual and erect image. And no matter what, where the real object is. So this confirms it. And yeah, that is problem number 1 there. Problem number 2 is for a +5 lens. So you draw it out, draw the axis and the lens. What is the location of the image? Well, I don't know, but we know the object is 10 centimeters from the lens, so that's minus 10 centimeters. The object has a height of 4, so then you do the L plus D equals L prime again. So this N is 1. You can call it N prime also 1. 1 over minus 0.1 gets you minus 10 virgins plus 5. And so what do you get? X prime is minus 0.2. And so that's 20 centimeters to the left of the lens, right? So that's double the distance of where the real object is. So I notice over here. How did I know that the line goes this high? Well, I calculated m is x prime over x, and that's negative 0.2 over negative 0.1 gives you a plus 2. So it's twice the length. So if the original height was 4, because it's the magnification is plus 2, you have a height of 8. Cool. And so hopefully you guys can kind of see how I set things up. I draw it out, then I write the equation below it, and then I plug in what I know and solve for it. So I know I'm going kind of fast, so I apologize if it's a little fast, but let me know if there's any questions you have. And also, I didn't do this too much in previous examples, but let me visually show you what's going on with vergence. Because remember how I said vergence is kind of like, it kind of talks about, is a measure of curvature. So if we have, and in this, when you're talking about objects, the vergence is the curvature right before it hits the lens. So this object had a vergence of minus 10. And that makes sense because it's diverging before it hits the lens. And so right here, you would call that, this curve that I'm kind of bolding, this L is minus 10, right? So what happens to that L of minus 10? Well, this power, the positive lens, right? If there was no lens, the rays would go like that, but instead it kind of, let me use a new color here. It kind of bends the rays a little bit like that, right? So, but it was not enough to make it converge and form a real image. Instead, the vergence kind of just, it's still the emerging vergence. So the vergence of minus 5 is the vergence right when it leaves the lens, right? Right here. So hopefully you can see that the vergence kind of changes, and when you trace it back, when you trace the lines back, you get a real object. No, what am I saying? You get a virtual image. You have a real object, and then it diverges. You have a plus 5, and so that vergence changes and you get a virtual image. But hopefully, I think, I wish I had explained this in previous videos, but this is really what's going on with the vergence. The vergence before the lens gets altered because the plus 5 lens is a vergence altering system. And so this new vergence that emerges is minus 5. And of course, when you measure vergence from far, far away, like here, the vergence is different, but you're really concerned with the vergence right when it hits the lens and right after it, or the lens, right after the lens. So eventually, of course, light will get really far and then it changes to 0, but we don't care about that. So yeah, that is the visual representation of vergence, what's going on. And yeah, so then ray tracing, the same rules apply for a thin lens. So I have a video on that if you haven't watched it. I deconstructed the ray tracing, so hopefully to visualize it a little better. And the center of the lens is used instead of the center of curvature, like the center of the uh, resultant lens kind of thing. And then you have a focal and you have a focal point and second focal point, and this object and image relationship should very much look like the other one in the previous section, where you have a real object and a real inverted image. Yeah, all that stuff it's just the table in the other one talks about minified and magnified. So, but the idea is the same. So these are the most important cases, like kind of the one, what that means is like the most relevant. Like we saw 6 cases, but these 3 are the ones that are most important that we see in like more practical settings. So like the eye is like, oh, I also made a video about the eye, how we can use optics for optometry. So that shows that an eye is really using a real object to reduce a real inverted image. And then we have magnifiers for plus lenses, and then we have negative lenses for certain things that we can use, like Fresnel lenses. You haven't learned that yet, I think. Placed on the rear windows of vans. Oh, actually, you did. It was in the prisms. Should be. Maybe it's not. I don't know. But some additional special cases include magnification equals +1. So what this means is like if you happen to have an image right at the vertex, nothing changes. Like because it's so close to the lens that the divergence doesn't really change. So you can say that L is equal to L prime, meaning that M is just 1. I remember something that was like this on the test, so hint, hint. I don't know. Maybe it'll be on it. I don't know. Magnification is -1 when x prime is equal to negative. No, wait. Yeah. When the object and the image are both 2 focal lengths from the lens. Yeah, that's when m is -1. So if the real object is twice the focal length, then the image will be twice the focal length and inverted. So same idea with the negative lens there. So that's kind of cool. Then the distant object, this verbiage is the same as the previous chapter, and you have a distant object that is presented to a thin lens, so the idea is the same. Okay, so with the distant object, the concepts to know here are that 1, the image position will be in the second focal plane, and so with a minus lens, that's going to be over here, right? Because remember, with the minus lens, this is f, therefore f prime's on the object space. Just adding this little piece in, I forgot to say it when I was talking about this problem, but then I deleted the problem. But this distant object can kind of be viewed is very similar to a parallel light because of how far it is, and that is the reason, that's the basis of this concept of why it ends up on the second focal plane. It's because it's almost as if it's parallel rays. So that hopefully that makes the connection between that is a distant object, but since it still is an object, it can be defined by an angle of subtence, meaning the angle that creates from the optical axis. And since it's treated like it could be viewed as a parallel light, it falls on the second focal point. The image size and orientation can always be found by drawing a ray from the object through the center of curvature, C, and that's right here. This is C, and the image size can be found using the relationship of this. So typically a problem will give you theta, And you will need to calculate f using f equals negative n over d. So with this problem, you have minus 1 over minus 2, because minus 2 is given, and then this is assumed in air. So you get positive 0.5 meters. You plug that into this equation now so that you could solve for h plus, and that's the first part of the answer, where it says what is the size. And then for position, you have to say, oh, well, the position is the second focal point. This is one of those instances where x prime equals f prime, and f prime is equal to n over d. Oh, sorry, n prime over d, and that's going to be, again, 1 over minus 2, so you get minus point. And that makes sense because it should be negative because you expect it to be over on the left side. And that's distant object. Last thing is Prentice's rule. This is kind of like how glasses work too, where a plus lens can be thought of as two prisms base to base. So you have this, and that essentially will act like this, right? And so minus lens is like two prisms upside down, or apex to apex, and so that is essentially like that. So viewing through an off-center point, when you're not through this or this is the center of the system, right? If you're not through that, you might get unwanted prism. So if you recall, like prisms kind of just change the whole image, moves everything, shifts it over a little bit. Prentice's rule allows you to calculate the amount of prism using this equation. The amount of prism right here is equal to the amount of decentration. So how far are you from the center in centimeters times the power of that lens itself. So this is kind of like your amount of prism, how much it moved is equal to d, little d, times diopters here. So a patient with an interpupillary distance of 60 is given a pair of -3 lenses with a 70 millimeter PD. So what that means is, so the PD is like the distance from each pupil. So if a patient has 60, right, their eyeball is like that. But they're given a pair of -3 lenses, so that kind of, if everything was perfect, right, they should be looking straight through the middle. And that's why we want to look through the middle of our glasses. That's why, like, if you're ordered glasses or as an optician, you dot where their pupil is, so that they have the best vision through the middle. And so the glasses they messed up, and they said the distance between the glasses, they made it kind of too far, like this. So, right? Like, let's see. Yeah, they moved it. And it's lagging. They moved the glasses, and the PD is 70, right? And assuming that they were moved kind of equally, the difference that it moved for each eye is 5. So that's what they mean by decentration, right? the decentration for each eye was 5. So you can now calculate the prism that is induced for each eye. If it's 5 millimeters, right? That's really 0.5 centimeters. And then, because it wants decentration in centimeters, that's just how the equation works. And then diopters is going to be -3. And so the prism that you get is minus 1.5, the little triangle up there for prism diopter. And what base are they looking through, right? If you kind of can visualize this triangle, they're looking through this triangle, and that's base N. This eye is also looking through this triangle, and that's base in because the base is going in towards their nose, as opposed to a base out means it's like the base is pointing outward. This would be a base out, but this is base in. So you'd say, what is the direction and amount of induced prism for each eye? It'd be 1.5 base in. So that's kind of the new this is a concept that's in this thin lens chapter because it's very much related to glasses. So let me know if you guys have any questions on Prentice's rule, and that's pretty much the end of this chapter. So.